Hey y'all, it's Miss Johnson. Here's another video I've owed you for a while. This is the physics and curvature assignment, or the curvature and physics assignment, whichever way I said it, same thing. This is when we're going to take a function that they've called the position function, kind of start just thinking of it as a regular function, and do some math about it, right? I'd rather do math than physics any day. It's a personal preference, and I'm going to show you how to do that if it's your personal preference as well. All right. The first thing, when they ask us to find the velocity equation, they're actually asking us to find the derivative. And when they, and by that I mean me, when I'm asking you to find the acceleration, I'm secretly asking you to find the second derivative. Pretty good. We'll go ahead and do that now. It's just the power rule. And then 12t minus 18. We did the power rule twice, right? When we found the first derivative, we take the derivative. We find the second, we just take the derivative of the derivative. Nice. And now we just have to know that whenever they say velocity, they mean first derivative. Whenever they say acceleration, they mean second derivative. And whenever they say position, they mean the original function. All right, find when acceleration equals 0. We're just going to go ahead and set our second derivative equal to 0 and do some algebra. All right, I'll let you finish that one out. Whenever we say find the, and this is actually a mistake. This should say position. Oof. When we say find the velocity, that's the second derivative, or the first derivative. When the acceleration equals 0, spoilers, this is 1.5, we're basically just plugging in 1.5 to our second derivative, right? Same thing here. Position is just our original equation. We're still plugging in 1.5, and we're getting numbers. And those numbers, have physical meaning. But as mathematicians, we're like, great, we were expecting a number, and lo and behold, we got one. Feeling good. I went ahead and put all this information down here. Let me put my head up here. I put all this information down here so we still have it. Let me put me way up. Okay. Now we need to do some interpretation. Now we need to say, when is the particle slowing down? Just like we did in the finding all key points assignment, we want to rewrite this question so that we know how to answer it, right? Things are slowing down when their speed is decreasing. It seems fair. Velocity is the first derivative. So now we're basically asking, when is y prime decreasing? We can look down here on our chart of relationships, and we can say that f prime is decreasing either when the original function is concave down or when the second derivative is negative. Out of these three things to investigate, pick one that you think is easiest and do it. I'm a sucker for algebra, so I prefer setting the second derivative to be negative and then solving for what makes that true. Again, that's a personal preference. When we're talking about changing between speeding up and slowing down, that means we're going from y increasing to y decreasing, which means we're looking for when y prime is at a maximum or minimum. So we can say, all right, when is the derivative at a max or a min? What's the maximum or min of this, right? We can also look at our chart and say, oh, well, when f prime is a max or a min, that means we're either looking for y's inflection point, or perhaps easier to conceptualize, we're looking for when the second derivative equals 0. I prefer this last one. Again, I like algebra, so I would set the second derivative equal to 0 and then solve. There are definitely other ways to think about this. There's definitely other ways to do this problem. This is my favorite way. When is the particle moving? That sounds like position. Forward, That sounds like it's increasing. So when is y increasing? We'd say the original function is increasing when the derivative is positive. And you can go on Desmos, figure out when this is true. You can use fancy algebra, figure out when this is true. But it will be helpful to do 9 first. And I probably should have reordered these, but that's how it is sometimes. When is the particle at rest between moving forward, which is increasing, and moving backwards, which is decreasing? It's in the middle of these when the original function has a max or a min. And the original function has a max or a min when the derivative is equal to 0. And we know what the derivative is. It's 6t squared minus 18t. And this we would either plug into Wolfram Alpha or plug into Desmos and figure it out. Or if we wanted to do fancy algebra, we would factor and go from there. Once we figure out the points, it's kind of tiny. Once we figure out the points where a particle is moving forward, where the particle's at rest, which ends up being like here and here or something. This is the wrong equation. That's the other assignment that I'm thinking of. Once we figure out, spoilers, that this is at 0 and 3, we know that kind of the 3 intervals are negative infinity to 0, 0 to 3, and 3 to infinity. And we want to say which ones of these is our particle moving forward, so which ones of these have positive derivatives, and which ones of these are moving backwards, which ones have negative derivatives. So basically we want to know which of these 3 intervals return a positive number when you plug something in the interval into y prime. Y'all, that's pretty much this assignment. If you've got questions, please message me on Teams, come to office hours, ask during class. The worst thing you can be doing is sitting at home doing math and feeling bad. Reach out to friends, reach out to me, reach out to the internet, but don't give up.